Hello, in this video we are going to go over stereochemistry. So you might be wondering, what does this word even mean? Well, stereochemistry is a part of chemistry where we look at the three-dimensional arrangement of atoms in molecules and how that can affect reactions or other chemical processes. So the reason we're interested in this is that carbohydrates can have different 3D arrangements of their different groups or atoms. And if that's the case, those are called enantiomers. We can also refer to these as isomers or stereoisomers that are mirror images of each other. Now, one really great example of enantiomers is your hands. So your left and right hand are enantiomers of each other. So if you face your palms together, notice that your hands are essentially mirror images of each other. Now, if you try to overlap your hands, so let's say you turn one of your hands over so that both palms are facing up. If you try to make your hands match, or if you try to superimpose them, they don't superimpose, they're different. Your thumbs are on opposite sides, your pinkies are on opposite sides, so they are enantiomers. So down below we have a figure of this. Now, if you do have mirror images that cannot be superimposed, you'll call those enantiomers. Just kind of a fancy word for that. We can also call them chiral objects. So we're learning a lot of words here today. Now, down below that, we have another example of two objects that are mirror images of each other. However, in this example, they can be superimposed on each other. So that would tell us that they are identical. So if you have two objects or two compounds that are identical, then we call them achiral objects. All right, so let's actually look at a compound that has an enantiomer, or we could also call that a stereoisomer. So down below we have glyceraldehyde. So this is a carbohydrate. And notice that they look pretty similar, but on the left we have L-glyceraldehyde. On the right we have D-glyceraldehyde. Okay, so both of these compounds have carbon in the middle, and then on the top they have CHO, which is an aldehyde, so it looks like this. So both molecules have that aldehyde group at the top. Both compounds have a CH2OH at the bottom. So that's a carbon bonded to two hydrogens and an OH group. And then in L-glyceraldehyde, we have an OH group on the left, but in D-glyceraldehyde, the OH group is on the right. Now on L-glyceraldehyde, the hydrogen is on the right, and in D-glyceraldehyde, the hydrogen's on the left. So that's the main difference. The H and OH are swapped. And that's why these two compounds have different labels of L and D, because they have different 3D arrangements of their groups. So these are enantiomers or stereoisomers of each other. So as we said before, a chiral object cannot be superimposed on its mirror image. So one really easy way to figure out if you have a chiral carbon, for example, is if it has 4 different groups bonded to it. So this is glyceraldehyde again. And this is actually D-glyceraldehyde because the OH group is on the right. And notice that if we focus on this central carbon, it is bonded to 4 different groups. It's bonded to that aldehyde group on the top, the hydroxy group on the right, the CH2OH group on the bottom, and then a hydrogen on the left. So because these are all different, this is a chiral carbon, and that means that this molecule does have an enantiomer, where the OH and the H are flipped. And we saw that on the last slide. Okay, so we'll call this chiral. Has an enantiomer. All right. Now, it is possible to have multiple chiral carbons in the same molecule. So the presence of a single chiral carbon, like in our last example, will give rise to stereoisomers, or what's also referred to as stereoisomerism. And down below, again, we have that example of many different chiral compounds in the same molecule. So this molecule has been repeated 4 times. So we've got the original here, and all of these are the same. But we're just going to step through the different carbons in the chain and determine if they're chiral or not. So let's start with the first carbon at the top. So this carbon is bonded to only 3 different groups, this oxygen, this hydrogen, and then the entirety of the rest of the molecule. So already we can say that it is not a chiral carbon because it's not even bonded to 4 groups. So we're just going to move down the chain and focus on the next carbon, carbon 2. Now, looking at what this carbon is bonded to, it's definitely bonded to 4 different groups. We've got this aldehyde, this hydrogen, this OH, and then the rest of the molecule down below. So that is definitely a chiral carbon. Now, if we just move down the chain to carbon 3, then we see the same thing. The top group is different from the bottom group. And then we have OH and H, which are also different from everything else. And then if we keep moving down the line, we can see the same thing for carbons 4 and carbon 5. They are both bonded to 4 different groups. Now, you might be wondering about this last carbon at the very bottom. Notice that it is bonded to 2 hydrogens. So if any 2 groups are identical, then that carbon is not chiral. So because the very bottom carbon is bonded to 2 hydrogens, that means it's bonded to 2 of the same thing, so it can't be chiral. Okay. So again, like we just saw, compounds can have more than 1 chiral carbon. So then that begs the question, well, is there a stereoisomer or enantiomer for every single chiral carbon in a molecule? The answer is yes. So the maximum number of stereoisomers that a molecule can have is 2 to the n, where n is equal to the number of chiral carbon atoms. Okay, so let's go back through our examples. Let's go to glyceraldehyde. Now, in this molecule, we only had 1 chiral carbon, which was right in the middle. That was the only carbon that was bonded to 4 different groups, right? And we saw that on this slide here. So that means if we plug that into our equation, 2 to the n is the number of chiral carbons, so that was just 1. So 2 to the 1 is just 2. So there are 2 enantiomers for this molecule. And we already know that's true looking at this figure. Okay, so now let's look at this example. In this example, we said there were 4 chiral carbons. So 2 to the n, where n is 4. Let's see, that would be 2 times 2 times 2 times 2. So we're just multiplying 4 2's together. So let's see, that would be, well, 2 times 2 is 4, so we'd have 4 times 4 is 16. So there are 16 different versions of this molecule, and those different versions just have the OH and H's flipped on each carbon. So you can imagine if we had an even longer chain, we would start to see tons of different stereoisomers. Okay, and we just did that calculation that this bullet point is talking about. So let's practice. Let's practice identifying chiral carbons, so carbons that have 4 different groups attached. And then we'll also practice calculating how many stereoisomers there are, or how many enantiomers there are. So I'm going to give you a molecule. And this will look pretty similar to some of the other molecules we've seen so far. So this is a carbohydrate. So how many chiral carbons are in this molecule? And once you figure that out, you can do the calculation to determine how many stereoisomers. And I just abbreviated stereoisomers because I ran out of room. So remember, you would plug in the number of chiral carbons into 2 to the n. So feel free to pause the video, try this on your own first, and then when you unpause, we'll go over it together. Okay, so in this molecule, we have 1, 2, 3, 4 carbons. Now, earlier we said that the carbon in the aldehyde group is not a chiral carbon because it's only bonded to 3 groups. Okay, so that one isn't chiral. But let's look at carbon 2. It's bonded to the aldehyde group on the top. It's bonded to hydrogen, OH, and then all of the atoms on the bottom will count as one group. So the top group and the bottom group look pretty different from each other, and those look pretty different from OH and H. So that has 4 different groups attached. Okay, so that is a chiral carbon. Now, let's look at carbon 3, and I'll use blue this time. So that carbon is bonded to the entire part of the molecule up above, which is very different from the atoms down below. And then it's also bonded to hydrogen and OH. So those are 4 different groups. Okay, so that is chiral. Now, if we look at the last carbon on the chain at the very bottom, remember earlier we said that that is bonded to 2 hydrogens. So that automatically disqualifies it as chiral. So this is bonded to 2 identical groups. So that is not chiral. Okay, so that tells us we only have 2 chiral carbons. So let's plug that into our equation. So 2 to the n, 2 to the 2, so that would be 2 times 2 is 4. So there are 4 different 3D spatial arrangements for this molecule. Now, if you're wondering what those look like, I can kind of quickly draw a couple of them here. So we've got our original molecule. So one of the stereoisomers would have a flipped OH and H on that second carbon. The third carbon could stay the same. So the only thing that changed here was the OH and H on the second carbon. Another version, I'm just going to abbreviate the aldehyde as CHO. Another version, the second carbon would stay the same, but the third carbon would flip its H and OH. Oh, I forgot the H on the other one. So that flipped. And the last version, both carbons would flip their H and OH groups, and that would be our last stereoisomer. So even though these molecules look very similar, the 3D arrangement of those H and OH groups is really important, and we'll talk about why in a bit. So let's do another practice problem. So remember earlier we said that carbohydrates are polyhydroxyaldehydes and ketones. And so far we've been looking at carbohydrates that have an aldehyde group, but what if we have a ketone instead? All right, so notice that we've got a ketone here instead of an aldehyde. So see if you can identify how many chiral carbons there are and how many stereoisomers exist for this molecule. So pause the video, see if you can figure it out on your own first, and then we'll go over it together. Okay, so let's start by counting all of our carbons. So let's see, at the top we've got 1, then 2, 3, and 4. Okay, so let's look at carbon 1. Is that a chiral carbon? No, it's bonded to 2 hydrogens. So that is not chiral. And again, that's because it's bonded to 2 identical groups, those hydrogens. What about carbon 2? Is that chiral? Nope, it's only bonded to 3 groups. The oxygen, the group up above, CH2OH, and all of the bottom of the molecule is the third group. So that also is not chiral because it's not bonded to 4 different groups. Okay, let's look at carbon 3. Is that chiral? Yes. So it's bonded to that ketone up above, the OH on the right, H on the left, and CH2OH on the bottom. So that is chiral. What about carbon 4? Is that chiral? Nope, again, it's bonded to 2 of the same type of group, so 2 hydrogens, so that is not chiral. Okay, so we only have 1 chiral carbon, so let's plug that into our equation for figuring out how many stereoisomers we have. So that was 2 to the n, so we'll plug in 1 for our 1 chiral carbon. So that means we have 2 stereoisomers, also called enantiomers. All right, so I think I'm going to stop the video here so you can kind of process and digest all of this new information. I know it's a lot. We also learned a lot of new terms today. In the next video, we'll talk a little bit about these structures I've been drawing. They're called Fisher projections. I will see you then.